Real-Time Operating System Series Part 2, RTOS is on CPUs. This is a discussion of what the CPU needs are for an RTOS. At the end of this presentation, I'll hit that on the final slide. All this up to that final slide is a background build-up. If there's acronyms you don't know, go watch the first part. And of course, go to ragingdisk.org, look up the NUFR operating system, the links to the Git repository. There are examples, there's documentation, everything you need right there in NUFR. So there are two categories I have for different computing complexes, and this excludes a lot of the computing complexes you can have. General purpose CPUs and special purpose processors. I'm going to divide the general purpose CPUs into three categories. Anything less than 32 bits, which is the 8 and 16. The 32 bits with no memory management unit, and I don't think there are 64 bits without memory management units. And then the 32 or 64 bits that use an MMU. The special purpose processors consist of mostly the DSPs. There's other things like networking processors, but DSPs are used for applications that require a lot of computing power that it's not efficient to do with a general purpose CPU. You can sort of program them like you would a normal general purpose CPU, but a lot of times you have to write these in assembly language to take advantage of the architecture. Some of them will let you write stuff in C, but I'm not going to get into the DSPs. Now I have three different methods of putting a CPU on a chip. Chip being an integrated circuit. Integrated circuit consists of transistors, resistors, capacitors, and whatever. These things are called devices. All the devices are on a single silicon substrate, and that single silicon substrate is the integrated circuit. You can also have hybrids, but system on a chip has the entire computing complex on the integrated circuit. It has the CPU, the RAM, non-volatile memory, which is the PROM, EPROM, flash, and nowadays it's flash. In older systems it was EPROMs or PROMs. It's a self-contained chip that has peripherals, interface controller, whatever. Second category is a CPU which is embedded in an ASIC. An ASIC is a custom-made chip. You can also throw into this category FPGAs. FPGAs are programmable custom chips where the program is determined at runtime, but CPU can be part of an overall ASIC because ASICs nowadays have such high density that you can embed any number of things in them. And of course, a CPU and an ASIC can do any number of things. Can connect to blocks in that ASIC. You can have multiple CPUs. Won't get into that. Let me just go to the third category. Say a standalone CPU is one where you have the RAM and the flash not located on the same substrate as the CPU. So the first microprocessors, obviously you couldn't pack in the RAM and the non-volatile memory. Just wasn't enough room. There wasn't a technology for programming the PROMs, double EPROMs that were in its chip. You could do that to a limited extent, but it was easier to. They did have CPUs that have that programmable capability, but it was easier to have a separate chip a lot of times that you could pull out, program, and stick back in the socket. But the standalone CPU concept now is used on larger CPUs, having RAM off board and having memory and stuff like that off board. There are 8 and 16-bit CPUs under the 32-bit CPU category. Now, real old CPUs, there are greater varieties than 8 or 16. It's just that we have 8 or 16 now, and the evolution of CPUs, the odd architectures that aren't 8, 16, 32, 64, not divisible by 8, have fallen by the wayside, except for things like DSPs. General purpose CPUs are going to fall under the 8, 16, 32, 64. But the 8 and 16-bit CPUs are prevalent still. You might wonder why something as old as the 8 hasn't been phased out yet. There are business arguments for keeping these old chips. They've got a lot of engineering. They've got boilerplate code, and the cost is really low. And of course, the power is really low on an 8-bit chip because you don't have as many devices. The less devices, the less power. But the new designs that don't draw on all this stuff, people are probably going to choose 16, 32-bit CPUs. So the 8-bit CPUs, I'm just going to toss those things out. They're too small to put any type of RTOS on, so I'm not concerned with them. 16-bit CPUs I'll cover later. Nowadays you don't see 16-bit CPUs as standalone like you did with the original 8086, which was a 16. Consider it a 20-bit 16/20. But I'll talk about that later. How do you size a CPU? But the older CPUs couldn't fit the RAM on board. Nowadays they can. So the 16-bit is considered a small CPU, and you're going to have everything combined into one little chip because you're going to have a lower cost solution when it's all integrated into a tiny ASIC rather than spreading this out. A lot of other reasons for that. So the 8 or 16-bit CPUs are the AVRs, the PICs, the MSP 430s. And the 32-bit CPUs having no MMUs would be like the ARM Cortex-M series, the MIPS 32 series. And by the way, these can optionally have MMUs. The 8186 was used before the ARM Cortex-M series. 8186 is considered to be a 16-bit CPU, the 8086 family, even though you can address up to 20 bits. The CPU bit width is a function of the width of the register and how you can, in a flat address space, what's your linear range. So 16-bit CPU obviously is 64K range, and what's driven the applications to require larger bit range CPUs is the fact that you have bigger code bases, more RAM. So you can easily grow out of 64K of addressable space. You go to the 32-bit range and you think that, I thought years ago you never outgrow 32 bits, but 4 gig is not as small as it used to be. So that has put us up to the 64-bit limit, which of course now we think we'll never break out of. The 32 and 64-bit CPUs that have MMUs, and we all know the Intel x86, the AMD 64 CPUs used in PCs, the higher end ARM Cortex A series, MIPS 64, Intel Atom, all these things are MMU equipped. Actually, the 8286 was the first x86 CPU which had an MMU, and that came out in the early 80s. So the need for MMUs has been around for a while. You need an MMU to host an operating system like Linux or Windows, where you have processes running in their own memory space, and if there's a crash on that process, it doesn't bring down the OS and anything else. The Larger 32-bit CPUs, as I've said, have MMUs, but I don't see that people actually build chips with these MMUs, because remember, the ARM chips and the MIPS chips are used by ASIC developers, and they have the option of equipping these chips with MMUs or not. It's kind of a cookie cutter type design, and there's not a lot of people that want to put an MMU in a smaller chip like that, smaller compared to 64-bit. So an RTOS target CPU can run on any 32-bit CPU and most 16-bit CPUs. It can run on it. Now, can is different than should. Why can't it run on an 8-bit? Well, you just don't have the addressing space to accommodate that application that you find on an RTOS. So an RTOS is more sophisticated than a scheduler, and I'll talk about the difference between an RTOS and a scheduler in following part to this series. But an RTOS is more sophisticated than a scheduler. It has context switching and other features like that. You run individual tasks, which are essentially threads. When you have an OS that can do that sort of thing, you're probably going to be targeting an application which is more sophisticated, which is larger, has more drivers, does more interesting things like having networking stacks, having logging, file systems, and these things take text space. I say text space, they take non-volatile memory to store the flash, and an 8-bit CPU, you just can't handle that size. RTOS, from the flash perspective, also from a RAM perspective, they just don't make 8-bit CPUs that can do that. And if they did, you'd run across other problems too. So people don't even think about that in 8-bit, because the cost is the most important factor in an 8-bit, and you start to waste cost for a small application on an RTOS, which people will look at and say, well, for what we're doing here, we really don't need this. Let's save some RAM and let's save some flash and toss this thing out and just use a scheduler. So the 32-bit, let's leave the 32-bit and the 16 bits for hosting RTOSs. And I'll talk about why you would choose one over the other in the next slide. So RTOSs really are, when we talk about an RTOS, we are, depending on the context, we're discussing something different. The definition of what an RTOS is varies depending on the context that the term is used in. So on the first level, an RTOS is any operating system that can run real time. And what I have in the second point of this slide is an RTOS is optimal for CPUs with no MMUs. There are real-time operating systems which work with MMUs, but depending on the context, a lot of times when you say RTOS, you imply that it's not using an MMU, that it's a smaller operating system. It doesn't reach up to that level of sophistication where you've got individual process spaces that run in their own address ranges that are virtualized, and that you can't direct, one process can't directly access another process's memory. That's not what people mean a lot of times when they use the word RTOS, even though the operating system that runs under that would use an MMU. So an RTOS is for a smaller CPU, but like I said, I'll talk about the differences later between a scheduler and an RTOS. So an RTOS being bigger than a scheduler and having more features, it will naturally run in real time. In other words, it will be able to comply with real-time contractual software targets, deadlines, which if you don't hit will constitute a failure of the system, which I covered in part 1. It's easier to do that in a smaller environment, a more controlled environment. And so it's just natural that any small OS can handle real-time capability. Not always true, but the two usually go hand in hand. So all this discussion brings us to the last slide here, and the last slide is, why would you use a 32-bit CPU for an RTOS? Why is this preferable over a 16-bit CPU? The answer is that 32-bit CPUs usually, and this isn't always true, but they'll have features that 16-bit CPUs don't have. So when you have a 16-bit CPU and a 32-bit CPU, that's a rule of thumb categorization of sizing of a processing core and the features that go along with it. So you have to call a CPU. You've got to call a CPU something. You've got to categorize it some way in terms of sophistication and capability. So a 32-bit CPU will always have these, as far as I know, will always have these three features, these three bullets. Crash exception handlers. These are types of software exceptions that when you hit a illegal address, when you have you try to access a memory address which is out of range, these things will the hardware and the CPU will automatically vector over to a software handler, and that constitutes a crash. This is valuable in troubleshooting a problem that you have, because if a system doesn't crash, it's off the rails, and you're not going to catch the exact configuration you're in when that problem happened, because the problem will rear its ugly head again. So these things, even though for software developers, you dread getting a crash report, try to imagine life without them, because you still have the same problem without the report. So software interrupts apart from crash handlers are also valuable. The original Motorola 68000 series had what we call traps. ARM has called an SBC instruction. The old 8086 had an int software interrupt instruction. All these things are used in kernel developments, and it allows you to change modes in the CPU, hardware modes, and that helps creating like a wall between your kernel and your application space, even if you don't use an MMU. So the other whistles and bells that you get on 32-bit CPUs are things like JTAG interfaces, etc., etc. Now, if you have these features on a 16-bit CPU and other features I didn't list here, more sophisticated type of interrupt handling, interrupt vectors, then that 16-bit CPU is usable for an RTOS. I mean, but nowadays, and this wasn't true years ago, like I said, like with the 8086 being an exception, nowadays 16-bit CPUs don't generally have these features because the design of them is targeting a smaller, cheaper, lower power environment, and they need to get rid of as many features of the CPU in order to trim it down to meet those requirements. So this is why you find that RTOSs are on just about always, you find them on 32-bit CPUs and not on 16 bits. Of course, NUFR runs on a 16-bit CPU. It runs on MSP 430, MSP 438X, but uh, these smaller CPUs, since they're so starved of RAM, flash, and other resources, the average RTOS, which takes up more space than it should, in my opinion, when you stick it on like an MSP430, and those older MSP430s only have 4K of RAM, guess what? You can easily chew up 3K of RAM just hosting your RTOS, and that leaves you very little RAM for applications. And so people look at that and they say, well, this just isn't making sense. And the same thing with the flash too. The RTOS will consume a lot of flash space, and you're left with little left over. So the 32-bit CPUs, which became popular in the, say, mid to late 90s, and they pushed out the 8186 and replaced those with, say, ARM7 TDMIs. At the same time, you started seeing RTOSs instead of schedulers popping up all over the place. So the RTOS and the overall embedded app require these features. The sophistication of the systems that people are making demand that you have a means to develop this quickly. You have a way of tracking down bugs which occur. You've got a way of segmenting your application spaces so that you can architect an application or a process or a task. Let's just say a task on this size of a processor. You can create a task as a standalone unit that's not coupled with the rest of the code base. And this is what RTOSs bring to the table. So the 32-bit CPUs will be the prevalent target for RTOSs as you go out on the internet and start shopping around. So in the next episode, I will cover the differences between the scheduler and an RTOS, and you won't want to miss that. Until then, go and download NUFR off the GitHub, and I'm sorry, not GitHub, but go get the Git repository, get the documentation for it. There's reference examples on ST micro boards, on MSP430 boards that you can buy for a few dollars. You got an entire make environment. All the tools are free. Just buy invest in the discovery boards or whatever, and you can be up and running in a few minutes, debugging with GDB or some other JTAG based debugger, and you'll learn a lot about RTOSs. You also have a really good operating system that you can use at work, use as a hobby, use on small, larger CPUs. Spend your time doing that and come back and join me for part 3. We'll see you then.